Ahmedabad. With an extensive career of over 20 years at Hughes Network Systems USA, Professor Vashavada contributed to the design, development, and deployment of GEO, MEO, and LEO satellite systems and holds 12 US patents translating communication and DSP theories into real-world satellite applications. At Dhirubhai Ambani University, he teaches courses such as Introduction to Communication Systems, Advanced Digital Communication, Next Generation Communication Systems. He has also played a central role in advancing research at the institute, serving as PI or co-PI on multiple Department of Space Government of India funded projects with support exceeding 1.25 crores. In 2020, he established the CSPMI lab with ISRO funding, which basically drives 5 active research projects and supports a team of JRFs, including MTech and PhD scholars. So we are glad that you have accepted our invite, and it's over to you. Thank you.
Thank you, Professor Rajender, for inviting me to this FDP and for this nice introduction. So I'll share my screen and get started. Okay. So my topic for today is just an introduction to information theory, the classical information theory and classical communication, specifically the digital aspect of the communications. Okay, so that is the topic of today, and then I have 6 other lectures subsequent to today that I'll be focusing on other different aspects of classical communication theory. So for today, there are maybe 5 sections. I'll be giving an introduction and overview. Then we'll be looking at some general models and motivation and functionalities. So as Professor Rajender mentioned, I have done MS and PhD from Virginia Tech, and then I did B from LD Engineering College. I was with a company called Hughes Network Systems until 2016, and then since 2016, I am with DICT. At DICT, my research interests lie in the intersection of wireless and digital communications, as well as signal processing, machine learning, etc. And my students and I, we work on developing new algorithms, and we study their properties and their applications. Okay, for this particular course, FDP, there are some really nice books that I will refer you to. The textbook by Upamanyu Madhav is a very good introductory level treatment to communication systems. There is another book by by Joan Proakis. It focuses on digital communications. And then some subtle aspects of information theory combined with some statistical inference and machine learning by David McKay. These first 2 books are freely downloadable. And then the book by Joan Proakis and also by Leon Couch. These are all excellent books that you can refer to maybe from your library, etc. And there are some other reference books that I will provide. The book by Sklar, by Haken, by Stephen Wicker, and by Stephen Wilson. These are all some of the excellent books that I have benefited from, and I urge you to refer to these books to understand this topic in further detail. Okay, so let us look at some of the basic questions. In fact, the first question that I'll give to you, it formed the basis for the entire theory of communication and information that got developed about 75 years ago at Bell Labs in New Jersey. This was actually an outgrowth of World War II. There was some problem given to the engineers and the scientists that were working at Bell Labs. And one of those mathematicians, actually, he was working on cryptography, and he developed a theory of encryption and secrecy preserving message transfer. And that eventually led into develop this theory of communication itself. And that has actually transformed. It was a paradigm shift for the entire communication system design and engineering. And it actually, even today, continues to drive and continues to lay the foundation and the framework of today's communication system, be it 4G, 5G, satellite communications, any type of wireless or wireline communication, whether it is through fiber optics or whether it is underwater, underground communication, etc. All the times that we communicate through some electronic device, this mathematics that we will be looking at in further detail later on has formed the it continues to influence those design aspects. And believe it or not, the entire theory of modeling the communication systems and information systems grew out of a very simple question. This mathematician that I just mentioned, Claude Shannon, he took this problem that I'm giving you as a base, and through that base, he developed this entire wonderful, nice mathematical theory. That question is as follows. Suppose the bicycles are made in a factory and we know that they are defective with a probability of 0.1. You inspect 10 cycles made in this factory. What is the probability that 3 out of these 10 cycles that you inspect turn out to be defective? Does anybody know the answer to this question? It's basically a probability theory question. It just asks you to think in terms
The
of.
participants may type their answer in the chat box.
The probability cannot be 3 because 3 is bigger than 1. So the answer has to be less than 1. It's not 0.01 either. It's not 0.3. It does not use conditional probability. No. So I'll give you the answer. If you know binomial coefficient, it makes use of that. So basically the answer is 10 choose 3, and then that number gets multiplied by 0.1 to the power 3 and 0.9 to the power 7. 7 cycles are not defective, and the probability of each of that event happening is 0.9. So you multiply 0.9 7 times, so you get 0.9 to the power 7. And 3 cycles are defective, so you get 0.1 raised to the power 3. And that gives you the probability of one particular event in which 3 cycles are defective and 7 cycles are not defective. But the overall probability is the sum of all such events, and there are a total of 10 choose 3 such events, and so the final answer becomes 10 choose 3 times 0.1 to the power 3, 0.9 to the power 7. Now this is a problem that comes out of classical way of looking at the events. Here the problem is just representative in nature. You can actually cast this completely in terms of bits. So suppose you have bits in the classical sense, not qubits, but classical bits. And let's say the probability of 1, the probability of occurrence of 1 is 0.1, and therefore the probability of occurrence of 0 is 0.9. And the question is, what is the probability that when you take a sequence of 10 such bits, 3 out of those 10 bits will be 1? Exact same problem, and the answer is also exactly the same. And that is the way to think about classical information transfer via bits, via zeros and ones. In quantum world, that calculation would change. Now, again, in the classical world, we can answer this question: how many binary strings there are? If you take, let's say, instead of 10 bits, suppose you go to 100 bits, 0.1 kilobits, how many such binary strings you will have of the size 100 bits? And let us now assume that zeros and ones are occurring with equal chance, with a probability of 0.5 each. So then what would be the answer to this question? What are all the possible ways in which you can have a binary string whose length is 100 bits and zeros and ones are occurring with equal probability? So Dr. Swati Jadhav gave the right answer. The answer is 2 to the power 100. Now, that number may seem huge, and it is indeed huge, because if you think of some large numbers, and maybe one such large number that I will tell you is the age of universe, right? The universe is very old. The age is 13 or 13.5 billion years. If you take the age of universe, not in years, not in months or weeks or even hours, but if you take the age of universe in picoseconds, then that number is 1/4 of 2 to the power 100. Right? So 2 to the power 100 is a humongous number. And what is maybe surprising, what you may not have realized until the time that I'm telling you this, is that even a very small information size of just 100 bits is one out of nearly countless number of possibilities. I'm telling you here an information size which is only 100 bits. Now look at your email inbox, or more maybe WhatsApp, or whenever you are surfing the web or Instagram or YouTube, you are uploading or downloading information content which is far bigger in size, right? You have data which is not in just fraction of a kilobit, but in multiple megabytes and gigabytes. So if you replace this 2 to the power 100, this number 100 in the exponent, with megabytes, right? So it's like not only 2 zeros followed by 1, but maybe 6 zeros followed by 1, multiply by 8, that will give you 1 megabyte, and you have multiple megabytes. Or when you're downloading or uploading videos, the content is in terms of gigabyte. So if 2 to the power 100 is such a huge number, 2 to the power a million or a billion is just unfathomably big number, okay? And the way to get astounded by this is that we don't think twice about it. Right now you're looking at my slides, you're looking at maybe my video, and you say, okay, fine, this is all good. I mean, nothing amazing about it, but this particular information content that you're looking at is extremely rare to occur, okay? In terms of all the possible ways that the bits can flow to your computer and your devices, out of all of those possible ways, which is a humongously large number, you are looking at one particular sequence of bits which are getting translated by your WebEx into this video stream. That's extremely rare event to occur, right? And the reason why it is happening is because our language follows the rules of grammar. Our videos are and images are, systematic in nature. But in terms of just transmission of bits, if you consider all the possible ways that the bits can be generated and transmitted, and you randomize this transmission and generation, the number of possibilities become astoundingly large. And that is the way that engineers have realized that, when you get some information which is, let's say, 100 bits or 1,000 bits or 1,000,000 bits or 1,000,000,000 bits, maybe all of those bits are not real in some sense. What do I mean by real is that those 1,000,000 bits or 10 million bits, they are all not random. If they are all random, then I would need to store all of them and I would need to transmit all of them. But our rules of grammar, our rules of language, our even the implicit order that is there in our life and in our world kind of prevents most of those random realizations to ever occur. And so an algorithm which is aware of that will never reserve memory or will never reserve any bandwidth to transmit those possibilities which are never going to occur, right? And that has allowed the engineers to do data compression and data storage, because without that, our storage requirement, our transmission requirement would become just impossible to manage. Okay, so in the classical communication systems, classical information theory fundamentally benefits from this realization that the information that we transmit, because it follows certain systematic rules, it is not all random, and therefore it can be efficiently compressed and it can be efficiently stored. Okay, so that is one of the realizations that has driven the development of communication systems and even storage devices. Communication and storage are two facets of single coin, right? Um, the servers of Google and IBM and Amazon, they store information, but that information is not in silos, right? Ultimately, that information has to be communicated. And so communication and transmission and storage, they are all interconnected, as we will see as we progress in this course. Another very surprising thing is that the data rate, let's say in bits per second, which we are all familiar with, if we get the desired data rate, we are happy. If we don't get desired data rate, our communication link suffers. We don't get the high quality video. We are not able to listen to the conversation over the phone, let's say. I hope none of you is having that hard luck, but in case if you're having that situation where your data rate drops, then most of what I say would be not intelligible to you. So data rate is something that we today know very well. But what that mathematician, Claude Shannon, uh, back in the early days after World War II at Bell Labs, figured out is that data rate is intimately connected to the bandwidth, the spectral width of the signal that you are transmitting for communication, and also how much power that signal gets received at the receiver compared to the power at the receiver of the noise, right? So he connected all these different parameters in one single equation, and that equation for last 75 years or more than 75 years now um, is considered to be the most elegant and the most powerful equation ever written, not only in communication system design, but in general in the entire information and communication technology. In fact, that paper by Shannon is one of the most downloaded paper, most referred paper in the annals of information and communication and computer science. And that equation is exactly what I have written here, that data rate at the most is equal to the bandwidth times logarithm base 2 of 1 plus signal power to the noise power, or signal to noise ratio. Okay, so what this equation says is that if you have certain bandwidth in W in Hertz, then at the most, the data rate that you can transmit is, I mean, suppose signal power PS is same as Pn. So this PS over Pn becomes 1. So the quantity inside the bracket becomes 2. Logarithm base 2 of 2 is 1. So in that case, the maximum data rate that you can transmit is simply equal to your bandwidth. Okay. So if you have bandwidth of, let's say, 1 kilohertz, then you can transmit 1 kilobits per second. That's it. You can try transmitting more than 1 kilobits per second, but it won't help you. Your message will be garbled. If you transmit 1 kilobits per second or less than 1 kilobits per second, then you can be sure that even though there is noise, even though the bits are getting corrupted by the noise that is there in the environment, the noise that affects the antenna of your phone, let's say, or the noise that is there inside the electronic circuit that gets heated up when you power it on, the noise generated by that thermal mechanism, the thermal noise, even in the presence of that noise, all of your bits are going to be received accurately and correctly. Okay, so this is the fundamental equation. And clearly, if PS is not equal to Pn, then this logarithm part changes. If hopefully PS is bigger than Pn, and then the data rate becomes some multiple of bandwidth. So this is one of the powerful equations, and that actually the derivation of this equation actually comes out of this faulty bicycle problem that we just looked at. Shannon developed this entire theoretical framework by extending this binomial probability function that we just looked at. One another thing that I would say, and that this is the topic that we will touch upon when we look at digital modulation receivers, their optimal designs, is that, you know, practically all of us, either directly or maybe through some relatives, have experienced the unpleasant feeling of going to take the RT-PCR test maybe a few years ago when coronavirus pandemic was spread all over India. And believe it or not, it's again something very striking that the mathematical theory of the design of a communication receiver, the classical communication receiver, when we go over it, and actually maybe just today I will give you one problem related to that, is very much similar to taking an RT-PCR test. So when we design a receiver, especially to optimally receive the data bits or data symbols over a noisy channel, that problem, you are able to think of it properly and you are able to solve that problem in an optimal manner by casting that communication process in a manner which is very similar to what we humans deal with in our daily lives. Okay, so that is the topic of Bayesian theory as it influences the communication systems, but in the larger sense, AI/ML methods as well. Okay, there are a few other things. There's an eigenvector-based linear algebra that has also driven the communication system design, especially as it transitioned from 3G phones to 4G phones. We will not get into that too much, but the next topic is the topic of error correction coding, which is practically, given that there is all types of noise and fading and disturbances and corruption that the signal, let's say emitted by your phone going towards the base station experiences, then what can you do to somehow try to overcome the effect of the noise? And again, in the human context, we have experienced this problem, right? When we are in a party and there is a loudspeaker with loud music in the background, and especially if you are close to that loudspeaker, we can't hear what our friend is trying to tell us. And so today's communication devices have this inbuilt error correction mechanism that tries to recover the transmitted information even when a lot of the transmitted bits are either received wrongly or they are erased. Sort of like what happens in a noisy room. You're trying to hear what your friend is telling you, but half of what he's telling you, you can't hear well. Sometimes you can still make out what he or she is telling you by listening to what they said before and after the part where you couldn't hear well, right? Suppose they said, let's say 3-4 sentences to you, and let's say the middle sentence got corrupted because of this music. If you knew the first sentence, if you knew the last sentence, and if you maybe got some little hint of the middle sentence here and there, your brain is very smart. It will piece together the missing information and recreate what your friend has said, right? That is essentially error correction. What your friend told you, that message got received erroneously, but there is a very nice error correction mechanism operating within all our brains. As long as the information is not corrupted too much, it can do some correction. And this happens all the time. Like suppose if I wrote this with some wrong spelling, you will be immediately able to say that there's some spelling mistake. Or maybe there was some grammatical mistake in this bullet number 7. Again, there will be a flashing red sign in your minds and you will say that some grammar is wrong here. We do this all the time. It doesn't even stop at spelling or grammar. It goes to the higher level processes, right? If somebody tells you something, but there is something fundamentally, logically inconsistent, then you point it out that, you see, you are telling this to me, but either you are pulling a fast one, you are trying to trick me, or you haven't thought it properly. There is a logical fallacy, right? So there are so many different levels at which the error correction mechanisms in our mind operate. And believe it or not, today the classical communication devices try to replicate a lot of the error correction and error detection processes that are human oriented. Okay, so that is a one topic that we will be studying. Okay, let us see. We have few questions that I'll give to you one by one. These are a little bit open-ended questions. How would you define the information? How would you measure it? How would you transmit the information? And suppose the information that you transmitted went through a real-world communication channel that is noisy in nature. Then how much of the information that you transmitted actually got received successfully at the receiver? Right? So these are some questions. And the answers to these questions are hard to obtain, okay, because the concept of information is an elusive concept. But just maybe over next 1 or 2 minutes, let me see if you have any thoughts regarding these questions. What is a good definition of information, or a definition which is precise enough so that you can pinpoint it, you can measure it? Unknown thing is information, okay? Collection of data, okay? Good. So when you say collection of data, then the question becomes, what is data, right? The unknown thing is information is a good answer. New thing, right? Correct. and we will actually get to that. If you know something, then it ceases to be information. Okay, that's a very good point. You can be informed only when you don't know about it. So unknown thing is the information is a good one. And we will be actually directly going to that aspect of the information later on. But then what would be a good way to measure the information? And what would be a good unit? Okay. So maybe what I'll tell you is that look at the example I gave you, that if you have a 100-bit long binary string, then it can represent 1 out of 2 to the power 100 different possibilities. Okay. So what is the relationship between 2 to the power 100 and 100? You have 100 bits. Those are bits, right? Zeros and ones, 100 of them. But using those 100 bits, we just now saw, somebody answered this on the live chat. Using those 100 bits, we can point to a total of 2 to the power 100 different unique items. Those 100 bits viewed as an address of a digital logic system, it can have total of 2 to the power 100 different registers. And those 100 bits will be enough to give indices to all of those 2 to the power 100 different items. And you see that the relationship between bits and the total number of possible distinct unique items that those bits can refer to is exponential and logarithmic. You go from bits to the total number of items through an exponentiation procedure. We took 2 to the power 100, correct? On the other hand, if you are in the world of this different unique items, then although there are so many, although there are 2 to the power 100 different items that you are trying to refer to, you need only 100 bits. So you took logarithm of 2 to the power 100 to realize that the actual amount of data that you need to, that is needed to represent those all those different addresses is only 100 bits, right? So the definition of information that we are going to look at maybe in the tomorrow's lecture will have both the things. The first thing is what few of you pointed out. First of all, it is something that is unknown at the receiver. And that notion of unknown is going to be represented again probabilistically. If I know with probability of 1 a particular outcome, then I know it precisely and you don't need to tell it to me over a communication link. Even if you tell it to me, it is not going to convey any information to me. I know that that is the case, right? Suppose I tell you that you are all joined here on this FDP on quantum communication, and I want to tell you something which is you should all listen to very carefully. And then I tell you that tomorrow in Gandhinagar at 7:37, the sun is going to rise. Okay? You will say that we are wasting our time in this FTP because this guy is telling us something we know for sure. Things that are known at the receiver cannot convey information. But instead of that, if I say that, tomorrow in Gandhinagar, in the early morning, there is a 90% chance of snowfall, then your attention will pick up, especially if you are from Gandhinagar, Ahmedabad region, because it never snows here. And I'm telling you something which, again, is not certain. I'm telling this to you with a probabilistic aspect that there is a good chance, 90% chance, but there is a 10% chance it may not happen, but a good chance that it may happen. Typically, it doesn't happen, but tomorrow it's going to happen, and then suddenly your interest picks up. So the thing that is unknown, and the more unknown the thing is, in some sense, we are getting more information. So that is one aspect of the information definition, and the other aspect is this exponentiation and logarithmic formulations. Okay, so those are some of the concepts that drive the classical information theory and classical communication systems. Okay, there is another aspect to information is the subjective aspect. What could be interesting to you may not be interesting to some other people. It may be unknown to both of you. So mathematically, there is same amount of information, but one person might say that there is a lot of information, other person might shrug their shoulders. So that subjectivity aspect is not captured in this mathematical definition that we will look at. A lot of AI/ML systems actually try to capture that aspect, right? Same thing can be of interest to somebody and may not be of interest to some other people. And so one person will say that this is highly informative, other person looking at the same thing will say it is not informative. Like when I watch Wimbledon, I'm interested to see whether Roger Federer wins or not. Or now maybe Alcaraz if you are into tennis. My wife doesn't care about tennis at all, right? The TV set is on. I'm glued to the TV set. She has no relevance. She just goes back and forth in the room. She's not worried about the score or who is winning, who is losing. So that the same information is being transmitted both to me and to my wife, but we make different use of it. That utility aspect of information is not going to be covered in this course, okay? But the randomness aspect of it, what is unknown versus what is known, is the aspect over which Shannon formulated the definition of information. The other two questions that we looked at, how much information actually can be transmitted and how much of it will get through, especially when the channel is noisy, very nicely relates to the notion of influence. Okay, this is again firmly in classical information sense. See, and so somehow all of this nicely connects to what we do, what our brains do all the time, right? We feel somebody's influence on us, correct? You may have had mentors, you may have had teachers, you may have had friends, relatives who have influenced you a lot. How did they influence you? Think of it. They did not influence you by pushing you or pulling you, although maybe when you were young, your siblings might have done that. But the influence happens over here. Even if somebody hits you or even somebody physically plays with you, that gets registered in your brain. More seriously, when somebody influences you, they influence your brain processes. A good teacher that you may have would have changed your belief system, correct? And the more fundamental change to your belief system, more you feel that you have been informed in a more significant manner. That notion of how much of the existing belief gets changed by the data that you receive is also captured by the classical information theory. That is the nice thing about it. In fact, many a times when I look at this math and when I try to understand it, because I still am understanding this math. It's very nice math with lots of different repercussions. It almost seems to me that I'm not doing math, I'm doing my daily life. Our brains are actually the best information systems that is out there. This Chat GPT and Google Gemini still doesn't come anywhere close to what our brains are capable of doing. They are the best information processors, they are the best communication devices also. Right? So that notion of how much the incoming data influences the communication receiver is an integral part of this theory. Somebody, I think, mentioned that a definition of information is the amount of data. It's that, but it's more than that. It's not just the data, but the data that influences your beliefs. That is what really counts as the information. And that entire topic mathematically becomes more interesting when somebody is trying to influence you by sending you some messages. But this communication channel comes into play and it twists and distorts and corrupts that message. And so what you get is not the original clean message, but the distorted version of it. And so now how much you are influenced, right? So that is the answer that we will get when we look at the mathematical definition of information. Okay, so now I will give you this problem that I just mentioned about going for a laboratory checkup and looking at the test results. So let us say that there is a test similar to this RT-PCR test for coronavirus to detect a disease, let's say C, whose prevalence in the general population is 1%, meaning that if you pick a random person, the chances that they have the disease is 0.01. Just like you did in those days, and maybe now if you have some virus or some infection, you may still do it, hopefully not as much anymore. But let's say you go to a lab and they do the test. No test is foolproof, right? So there is always going to be false positives, meaning that you don't have the disease, but the disease comes out positive. But let's say that the test mechanism is accurate enough, so the chances of that happening is only 5%. Similarly, let us say that the correct positive rate is 95%, meaning that if you actually have that virus in your body, the test will say with 95% chance that you have the disease. Okay? So far, so good. It's all something that we all understand and relate to pretty well. The question is that you go and take the test in the lab and the test result comes out positive. What is the probability that, given that your test result came out positive, you actually have the disease? See, if the test equipment was precise and there was no false positive and there was 100% correct positive rate, so this 0.05 was 0 and 0.95 was 1, then the answer is certain. I did the test, it came out positive, 100%, I have that disease. Or whoever person goes and does this. But the reality is that there is always going to be non-zero false positive and non-unity less than one correct positive. Now, when the test result comes out positive, you are not sure as much, right? It came out positive, but maybe you were one of those 5% unlucky ones, or maybe lucky ones. You really don't have the disease, but it still came out positive. So who can answer this question? Am I still connected or I'm just speaking in vacuum? Are you all there?
Yeah, we can hear you.
Okay. Okay, fine. I'll let you all work on it. But what 0.95 is not the right answer, and that is because of this prevalence rate. Only 1% of the population has the disease, so that kind of changes the answer. Anyways, let's move forward. Basically, this problem can be cast through this diagram. What this diagram says is that there is a world of causes. In this case, it is the state of your body, whether you have the infection, which is C equal to 1, or you don't have the infection. Okay, Professor Maruthi gave the right answer, 16%. Correct. Okay, so the world of causes have these states, right? C equal to 0, C equal to 1. And there will be certain probabilities associated with this. In our case, Q was 1%, 0.01. Now, we never have direct contact with this world, right? The state of our body is always going to be unknown to us. But the state of the body drives our behavior. If we feel uh, not well, then we go and take the test in the lab. And so from the world of causes, which is invisible to us, we go to the world of effects, which is visible to us. And the test result also is, in this case, binary. T equal to 0, T equal to 1. 0 means test came out positive. 1 means, 1 means test came out positive. 0 means test came out negative. Right? And interestingly, there are these red lines. In the problem that I gave you, both these red lines have probability of 5%. You didn't have the disease, C equal to 0, test still comes out positive with 5% chance. And when you have the disease, there was 95% chance of following the green arrow at the bottom where my cursor is. And so there was 5% chance of the test coming out negative. So in the real world, the connection from the unknown, invisible world of causes to the felt, realized, observed world of effects or evidences is connected by this noisy communication channel. If there is no noise, there is no problem. If you have the disease, the test will be always coming out positive. If you don't have disease, test will always come out negative. In reality, there will be always some mistakes, some errors. And so now you are in this dicey state. Your test result comes out negative, but do you celebrate or not? You want to celebrate, okay, I don't have coronavirus, but then there is a thing at the back of your mind that, oh, what if I still have the disease? And you know this, I don't have to tell in this in further detail, but this is real life, okay? My wife thought that she has thyroid, hyperthyroid, okay? She was telling me, no, I'm not feeling good. I have something. My family, my mother has thyroid, and so it's very likely that I have thyroid. She in fact said I have thyroid, not even very likely. I said, okay, let's go and do the test. My dad was a doctor. He's no more. He said she doesn't have thyroid because he had 50 years of experience, so he knew. But my wife was very sure, so we went and did her test at a laboratory. The test came out positive. So then she was telling me, see, I was telling you I have thyroid, and so we have to do something about it. I said, wait a second, my dad is saying that you don't have thyroid. Let's do this. Let's go to this nearby hospital. Let's repeat the test. We went there. There, the laboratory told us that you don't have thyroid. You see, at that point, we were totally confused. We didn't know whether she had thyroid, didn't have thyroid. we were just on this red and green lines, believe it or not. It's a real life situation that I'm showing here. But the amazing thing about this is that this is entirely a communication theoretic framework that I'm telling you. X equal to 0, X equal to 1 are the bits that the transmitter is sending. Y equal to 0, Y equal to 1, or T equal to 0, T equal to 1 are the bits that the receiver is getting. The receiver and the transmitter are not co-located, they are not connected. So receiver will never ever know for sure what the transmitter sent. And that knowledge would be fine if P was 0. But the real world communication channel, P, the probability of error, the red arrows are always there. Exactly the same problem, you see. I was telling you that the real world and the mathematical world of information and communication theory are deeply connected. And the type of mathematical thinking that a communication system designer engages in is the type of thinking that we do all the time, every time. But a communication designer takes this real world phenomenon and examines those phenomena thoroughly in a probabilistic sense, and then comes up with a theory which is optimal in some sense. If you get y equal to 0, what is the probability that x equal to 0 or x equal to 1? And that actually forms the Bayesian framework for the design of communication receiver that we will get into later on. There is another type of channel, again a mathematical model, where the transmitted bits undergo erasers. So what you get is either 0, 1 or eraser. And that also is a good model to represent the effect of a communication channel. And this question that I gave you, I think one of you gave the right answer. Maybe you can take it as a homework problem. Basically, you have to think of it in terms of conditional probabilities now. That suppose your test came out negative, y is equal to 0. What is the probability that x equal to 0? What is the probability that x equal to 1? And that becomes a basic test. And those are the things that drive an understanding of the classical communication theory. And it is through working out these problems that Shannon figured out that the fundamental equation that drives any type of communication system is this equation that we looked at. R at the most is equal to bandwidth times logarithm base 2 of PS over Pn. See this log base 2? Remember where it comes from? We said that if you have 2 to the power 100 different items, you need log base 2 of that to represent them. Believe it or not, that's something that we understand it very well is the same reason why this log base 2 is present here. Other parts of this equation, how they came about, we are not able to understand it as of now, but this is the fundamental equation, similar to equal to mc square equation in physics that Einstein derived. And in fact, engineers have written it in a different manner. They took W on the left-hand side and they called the ratio R divided by W as eta B, and they called the ratio PS over Pn as gamma. And then the equation becomes even simpler. Eta B is less than or equal to log base 2 of 1 plus gamma. And I have plotted it here. Because of the logarithm, the curve flattens out as you go further towards the right on x-axis. What is eta B and what is gamma? Eta B is called the bandwidth efficiency. How much efficiently you are using the spectrum that is allocated to you. Given a unit of bandwidth, if you are able to transmit a large number of data rate in bits per second, then this ratio is favorable. Eta B is high and you have a good spectral efficiency. On the other hand, this gamma PS over Pn is inversely related to the energy efficiency. If you ask for large value of PS for a given amount of Pn, if you want large signal power to maintain certain SNR, then you are becoming energy inefficient. This is also something that is quite relatable. If I want large amount of powers to be received at the receiver, I will need to make the antennas bigger. I will need to make power amplifiers either more efficient or bigger. Basically, the device will become inefficient. If it is battery powered device, the battery will get depleted very quickly. A connected device, it will heat up very much. Why? Because it is transmitting large amount of signal power. Basically, that aspect of communication design becomes inefficient. Why? Because as you ask large SNR, you require a large amount of power or energy, and that is never efficient. You want to operate your communication system at as low power, at as low energy as possible. Right? This is very understandable. The reason why this phone has become ubiquitous is because it is lightweight. I can hold it in hand and it never heats up as much and its battery lasts for long. But what if this phone was the size of a brick or it had massive antennas coming out of it? Then, well, maybe it won't be as much usable anymore. What is interesting is that y-axis is the eta B, spectral efficiency, x-axis is the inverse of energy efficiency. You want to increase the spectral efficiency, you want to go up on y-axis, but what this relationship is telling you, the Shannon channel capacity equation is telling you is that in order to increase spectral efficiency, you have to go rightward on x-axis, which means that you are becoming energy inefficient. Right? So that is the last thing for today. Spectral efficiency and energy efficiency. They are at loggerheads. They are fighting with each other. If you try to emphasize on spectral efficiency, you have to give up on energy efficiency. Or if you try to be energy efficient a lot, meaning that you use small power amplifiers, you use small antennas, you don't ask for too much power, then necessarily you will have to dial down on your expectation in terms of spectral efficiency, meaning that given a particular amount of bandwidth, you are not going to be able to transmit high amount of data rate in bits per second. Okay, so that is the last thing for today. There are other things that are maybe more of a detail that we don't need to get into. I think Professor Mehtarwal will be sending you the entire set of slides. So if you're interested, you can look at the rest of the slides that I didn't get time to cover. But I think that in terms of some introductory concepts, I think I have covered everything that I wish to do in today's lecture.
Okay, thank you very much for your session. And we'll be continuing with these concepts in coming sessions till Saturday. So he'll be with us till Saturday, covering these concepts in more details. So there are a few questions, probably, I'm not sure whether we have taken that or not.
Okay.
So the first question is, how much of the classical communication theory is relevant to quantum communication? So, if you see, this is kind of a brush up for some of the participants who do not have the electronics and communication background. So, if somebody has already studied communication systems, probably they can directly jump into the quantum communication theory. But since some of the participants, they don't come from the background where they have studied these concepts, that's why it's kind of a brush up. And for this particular FDP, we have chosen the syllabus which was prescribed by AICTE when they had their workshop related to quantum. So if you see the quantum communication syllabus which is prescribed by AICTE, this is a major portion where they brush up the classical communication theory, and that is why we will have around 7 sessions on this fundamental of communication theory. I hope this answers the question.
So if I just add a little bit to it, I think my understanding is that to be able to understand and appreciate quantum communication and quantum information theory, the first stepping stone to that is appreciating classical information theory, classical communication. Because if you don't have a full understanding of that, then you can't generalize to quantum world. And I hope that this lecture and the subsequent topics that I'll cover will help you do that.
Right. So there is, I mean, not a complete question, but somebody put BSc, BEC question mark. I don't know what.
Yeah, so BSc and BEC are the two channel models that I showed you. BSc stands for binary symmetric channel. Binary meaning that the world of causes and the world of effects, both are binary. You either have the disease or you don't have the disease. It's a binary phenomenon. You take the test, it comes out positive or it doesn't come out positive. That also is binary. So both transmitter and receiver are dealing in bits, zeros and ones. And it is symmetric in nature, meaning that the chance of false positive is 5% and the chance of correct detection is 95%, meaning that false negative is also 5%. Meaning that when you transmit 0, there is some probability p that it turns into 1. And that same probability applies when you transmit 1. The chances that 1 becoming 0 is also p. So there is a symmetry in that sense. So that's why that channel is called binary symmetric channel, BSC. BEC is that second channel I showed you where bits can get erased. It's a binary erasure channel, and there also it is prescribed with some probability of erasure.
Okay. So thank you, Professor Vasavada. We will continue with these sessions. I want to make one announcement that the WebEx link will change, which we have. So the link was same for last 3 days, but from tomorrow onwards, we will have a different link. So we'll be sending the emails. You will get a new link. So you are supposed to use the day 4 link for joining the remaining sessions. All right. I mean, we'll join again tomorrow at 3 p.m.
Okay. See you. See you. Bye.
And